maybe we can get going if you're ready, Peter.
Yes, I am.
Okay, good. So welcome back to the second talk of today's sessions. It's my pleasure to introduce Peter Fiebig from Erlangen-Nürnberg, who will be talking to us today about approximating tilting modules.
Well, thank you very much, Jay, and I'd like to thank the organizer for giving me the opportunity to speak. And I would also take the opportunity to thank the staff at IIS for doing their best, what they can to accommodating the members at the IIS in this very unusual situation. So thank you. I was a member last semester, not so anymore, but yeah, thank you very much. So my talk will be about tilting modules, like Simon's talk, but I will I will discuss tilting modules in a very different direction. So there will be almost no overlap. So let me just start with fixing some notation. So for simplicity, G is like in Simon's talk, a connected, simply connected algebraic group over a field K, which is algebraically closed, and we'll almost always assume that it's of characteristic P, which is positive, and T and B and G are as usual, so a maximal torus. And the Borel inside G. And I also denote by X the weight lattice. And inside here, I have the dominant weights. So that's all standard notation. And so for any dominant weight lambda, there's three types of, modules for the group that are of interest. Well, the first is the simple module. So this is the irreducible module with highest weight lambda. Then we have the Weyl module with highest weight lambda. And we have the tilting module, T lambda. That is associated to this weight lambda. And well, we are still kind of discussing maybe the basic problems here in this version of representation theory. So so the first basic problem is, of course, to calculate the character of a lambda. And this would be equivalent to giving the Jordan-Hölder multiplicity of the Weyl modulus, because the characters of the Weyl modulus are known. So if you know all these multiplicities, so this is the Jordan-Hölder multiplicity. If you know all these multiplicities, you deduce the character of the simple. Oops. Okay, this is a difficult problem, and it's solved for P big enough, and it's wide open for P not big enough, and the precise bound when P is big enough is unknown. So here, for every non-specialist, I should maybe say fixing the root system. Then there's a bound such that these characters are known for all lambda once P is bigger as this bound, depending on the root system. But we don't know what is going on for P smaller than this bound. We also have very few examples of characters that that are calculable but are not given by Lustig's character formula. And I think in recent years, due to work of Jordi Williamson, Simorich, and many others, the focus, I guess, switched a little. So we could also ask for the character of the tilting modules, which, because they have a Weil filtration, would be the same as the Weil multiplicities inside these tilting modules. So you can ask either question, and this is an equivalent. So both of these questions are equivalent. And it is known that the second problem actually solves the first. So at least for p not too small, if you know the characters of the tilting modules, you know the characters of the simple modules. And as you could see from Simon's talk, we have new methods to attack this problem. And Simon even wrote down a formula for these the characters of these tilting modules, which involve the p-Castaing-Lustig polynomials. And unfortunately, these p-Castaing-Lustig polynomials are still kind of unknown. I mean, we spent some time last semester at the IIS to discuss ways to calculate these p-Castaing-Lustig polynomials, and there is an algorithm, and we have many examples. But I think it's a general feeling that we don't have the algorithm yet that gives us the p-Castaing-Lustig polynomials. So I will come to that later. I mean, it's the guiding question of the talk right now. So I will discuss these questions in a different framework. Namely, I will translate everything into representation theory of the algebra of distributions. So supported the distribution supported on G. So in characteristic P bigger than 0, let's just assume that the characteristic of K is now P bigger than 0. This algebra of distributions, also sometimes called the hyperalgebra, replaces the universal enveloping algebra of the Lie algebra of G, in the sense that you can embed the representation theory of the group, the rational representation theory of the group, inside representations of this G. And this algebra is quite well known. Let me show you how to think of this. So to define it, we might actually first look at the Lie algebra of the complex group associated to G. And here we have Serre generators, E alpha, F alpha, and H alpha. So alpha runs through pi, which is the basis of the root system. And well, you all know the theorem of Serre, which says, well, the Lie algebra is generated by these elements subject to some conditions. I won't write them down. It's absolutely not necessary. So for n bigger than 0, you look at these divided powers. So E alpha bracket n is just the nth power of E alpha in the universal enveloping algebra divided by n factorial. F alpha is defined in the same way. So, and with H alpha, you do something a little different. So, sorry, H alpha, so define this binomial coefficient. So, and this is divided by n factorial. And so all these elements are in the universal enveloping algebra of UC. And you can look now at the constant form over the integers. So this is the subring in UGC generated by all these elements above, also E alpha to the n, F alpha to the n, and this binomial coefficients. So alpha is a simple root and n is bigger than 0 or bigger or equal to 0, then they are all 1. So this is an integral form of this enveloping algebra. And now for our field K, you obtain decay by base change. And this is the distribution algebra. So it is very similar than the enveloping algebra, but it contains these divided powers. And you see in characteristic P, we couldn't possibly define these elements in the universal enveloping algebra of the Lie algebra of G, because this n factorial might be 0 in K. But we can define it over the integers, over the rationals if you want, and then use these elements as generators in this algebra dz, and then obtain decay by base change. And now a well-known fact is that the rational representations of G, so I'm only looking at finite dimensional representations of G, so G mod representations of G, they in one-to-one correspondence and equivalence categories with the finite dimensional decay modules. Okay, so here in decay, we consider a lambda and T lambda and the Y module V lambda as representations over this algebra decay. And the nice thing is that you do have a triangular decomposition, even over the integers, where, well, dz minus is generated by the F alphas, dz plus by the E alphas, and dz 0, the E alpha to the n, and F alpha to the n, and dz 0 by these binomial coefficients in the H alphas. So that's a very nice thing, because this also gives you this triangular decomposition over K. And now a very natural thing to do is to look at the category OK, which is the category of decay modules. That are semi-simple for the 0 part, and locally finite for decay plus. But I don't assume that these modules are finite dimensional, so they don't come from rational representations of the group G. Well, for me, this is a very natural category now to consider, and I do think there's very few results on this in the literature. So the corresponding category for quantum groups was studied by Anderson and Mazurchuk, but there's not much to find about this category in general. I mean, most of the objects inside this category are infinite dimensional, so have nothing, I mean, they don't come from the group G. I do think it's interesting to study, and I think it's much easier to understand than the rational representation theory of G. So we're interested in OK finite dimensional. So these are the finite dimensional integrable objects inside this category. So In this talk, I'm kind of ignoring the question about the simples. I'm focusing on the tilting modules and the while modules. And it turns out they can be lifted to the p-adic integers. So a natural thing to do is now to consider the following modular system. So you have your field K down here, and then you have a map from the p-adic integers, which is contained in the rationals. And since the algebra of distributions is defined over Z, you also have the corresponding distributions, if you want, for the group scheme over the p-adic integers. You have this this algebra DCP, which sits inside DQ, which, by the way, is the universal enveloping algebra of the Q version of G. So we can now consider also modules over a DCP. And the most interesting category, for me at least, here to consider is, well, I call it also category O. This WF should stand for while filtration. So these are the objects that have a while filtration. So the while modules have a lift to the p-adic integers. So these are the DCP modules that such that DC0 P0 acts semi-simply, and I think that's actually not necessary. That so they should have a finite while filtration. The filtration by while module. So yeah, so there is a while module over in DCP mod, and also a tilting module, and you obtain the modules that we are interested in by base change. So our V lambda is so lambda is dominant. V lambda you obtain from this deformed version by base change, and also the tilting module. Also, this base change factor is exact because everything in our category is free over over CP. So so now we try to understand these tilting modules over the p-adic integers, and now let me tell you maybe the first idea that I would want to present in this talk. We are now interested in torsion. So torsion phenomena. So if you have one object in this deformed category, and you have a weight not necessarily dominant, then you can look at the following construction. So m delta mu, by m delta mu, I want to define, I want to well, denote the following subspace in M. So we have a direct sum over all simple roots and n bigger than 0, and we take the weight spaces in the simple root directions that lie above mu. And of course we have mu. And here two maps, E and F. So this is F, this is the map that I call F mu, and the map that I call E mu, and these are just so the direct sums of the maps E alpha n p pi and n bigger than 0, and F mu This is the F alphas, so transposed. Okay, well, it's the column and the row vector with these action maps of these elements E alpha to the n and F alpha to n in this distribution algebra. Okay, and if you participated in the program and heard my talk last semester, for me, this is a kind of hard Lefschetz situation here. You have, you can consider as the tilting module as being defined by the property that these F's act as Lefschetz operators on this space. We don't need this here, but what is important now is the torsion. So there's the following lemma. It's very easy to prove. The first part is that if we restrict E mu to the image of F mu, then this is injective. This is not so important for what follows. But the second property is more important. If we apply E mu to the image of F mu, then this, of course, sits inside the image of E mu. And this has a torsion co-kernel. So it's annihilated by some power of P. Okay. So once you know this, you can define certain subspaces. So this is all inside delta mu, a minimal subspace, and a maximal subspace. And inside here, something which lies in between. So how is that defined? Well, this is just E mu applied to the image of F mu, and this here is E mu of mu. So this is what we had before, and this here, let me just shortly say. So the maximal n that contains this minimal subspace such that the quotient is torsion. Okay. So there's a maximal such module, and this E mu lies in between these two extremes. And now the first theorem. The first part is kind of easy to prove. So suppose our intermediate subspace is always minimal. Then, well, this is the case if and only if M is a direct sum of Y modules. And the second, well, on the other extreme, if this intermediate subspace is always maximal for all mu and x, well, this is the case if and only if M is a tilting module, and the direct sum of indecomposable tilting modules, of course. Tilting is a tilting module. So these are the two extremes where you have the Y module and the tilting module on either side. And let me just draw a little picture, a kind of a naive, silly picture, which should explain. Yeah, it's really a little silly, but it might help to understand what is coming. So, so yeah, okay. Wait. Let's first let's say this is m delta mu, and then you have, say you have p somewhere here. So this is p times m delta mu, and then maybe you have p squared m delta mu here. And then you have this minimal submodule. Yeah, you have that sitting, oops, sorry. You have that sitting somewhere here. So let's draw it like this. So this is the minimal module. You obtain the maximal module if you kind of, oops. So this is the maximal submodule. And in between you have the module that's actually important. So this contains the minimum module, and then might look somehow like this. So this gives the actual intermediate module. Okay, so yeah. What is that good for? This point of view, it tells you that there's some space between between the y module and the tilting module, which is of course not very surprising. But I try to understand if this has something to do with this conjecture that generations exist. That was formulated by George Lustig and Jody Williamson, based on previous work on generations of simple irreducible modules of George Lustig. So, so what I want to talk about now are generations of characters. So generations of characters. So this is just a kind of philosophical idea. And I think no one really knows up to today what a generation of a character should really be, but one has a lot of intuition. So let's see, yeah, that worked out well. So the next slide you see here is the tilting pattern. So the tilting pattern for SL2, for A1. And here the prime is 3. And you should read it as follows. So red dot, this just means that the tilting module with highest weight lambda has the y module with highest weight mu as a subquotient. So the subquotients, the multiplicities are all smaller or equal to 1. And so here you see lambda on this line and mu on this line. And so, for example, if you look at some line here, for example, that means the tilting module with this highest weight has also this Roma y subquotient and so on. So you also see some tilting modules that are actually, if you look here, here's a tilting module that's actually a y module. It has no other subquotient. And so this is known from the early, from Dongking's tensor product. You can actually read off all these multiplicities. So SL2 is the only case where we actually know all multiplicities. And you obviously see some building principle here. It's easy to generalize this to 5. I mean, the prime number occurs here. You see these legs have length 3. These have length 9. Here would be one with length 27, and so. But I also want to point out, it won't play a role in this talk later, that in order to describe this pattern, maybe the easiest way is to think of a kind of dynamics, which reminds you of this billiard dynamics that Lustig and Williamson explained. So excuse the very playful way to say this, but if you want to give this pattern, you could say something like, well, let's have a ball. Oops. Let's have a ball with infinite energy running along this line. And every third step, it splits off a ball with energy 3. But every 9th step, it splits off a ball with energy 9. And every 27th step, it splits off a ball with energy 27. And a ball with energy p to the n is allowed to split off balls with energy p to the n minus 1 and so on. So I like to think of this picture dynamically in this way, because there might be some hint of how to think about these tilting modules, of how they create. Because you see something very similar but far more complicated in A3. So let me show you some A3 patterns. So tilting patterns for A3. So these come from a paper of Jens Jensen, and some correction to Jensen's paper were given by Alison Parker. So in SL3, if you look at G1T modules, you see some 2 basic patterns appear. So an hexagon and a star. So you should keep these 2 patterns in mind. And now the multiplicity of tilting modules, they are kind of given as follows. So here, this triangle, the big triangle, is the dominant chamber, the dominant cone. And here you have the Weyl group, affine Weyl group acting. Here, this would be a P translated hyperplane. Here you would have a P squared translated hyperplane, and here 2P squared translated hyperplane. And far above your screen would be a P cubed translated hyperplane. And you should read this pattern as, well, the tilting module with highest weight here has multiplicity 1 Weyl modules here, 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 and here. And here you see the linkage principle that Simon talked about also appearing. The affine Weyl group is actually generated not by the hyperplanes that you see drawn here, but by these P hyperplanes that are everywhere that I left out. So this is one example of tilting module multiplicities. Then you see the star occurring. And this is always, when you're far from the walls, these 2 patterns, they repeat each other. But if you're on the wall, then something strange happens. So this highest weight, it would like to have this hexagon pattern, but it can't, because here are no dominant walls. And so instead, there's something missing here, and you get some additional multiplicities here. So it's very strange and a little creepy. So this happens once you cross the first P squared line. And so this looks a little more harmless. So you would like to have the star here, but you can't, again, because some of the dots are not dominant. But then it gets more complicated. So here, green means the multiplicity is 2. And here you can think of, well, we have we have the pattern that we had before, this 4 alcove pattern, but we have another pattern, which is this hexagon. And if you now go up with this weight, this hexagon will move to the left, but in a very funny fashion. So first you have a star, and this creates this star, and this moves in this direction, this moves in this direction. And then, so that I think is the last example that I have, you have these funny things appearing, and then suddenly you have 2 hexagon patterns overlapping in a sense. But what this could maybe tell you that there is some kind of funny billiard going on where you have a ball going in this direction and this wall, it just splits off a ball in this direction, and then in every direction something happens. Okay, so the generations idea is the following. Let me go back to SL2 to A1. So if you look at the quantum group, you can also define tiltings and Y modules, but the multiplicities for the quantum group are much easier. They would look like this. So all these big parts would be missing. And so George Lustig and Geordie Williamson say, well, this should be a generation 1 character. And generation 2 character would allow all legs of length 9, but none of length 27. So that would be generation 2. And then here would have generation 3. Similarly, here, I mean, this is all generation 2. You would say this component here, and that's glued to the wall, is generation 1. And these 2 components are generation 2. And you see the generation 2, the contribution in generation 2, it moves in another way. And here you have a very strange contribution in generation 2. So I guess many of you listened to George Lustig's talk 2 days ago, and he said that these generation 1, generation 2, generation 3 patterns should come from tilting modules. In this case, he talked about irreducibles. For tilting modules for some Lie algebra or quantum group that is yet to be defined. And he gave examples. I mean, he gave a conjectural construction in terms of affine Lie algebras or affinizations of affinizations of affinizations of Lie algebras that should give these characters. So when I thought about this, I had a naive, different idea. I thought, well, if you look at this torsion, so let's go back to this torsion picture. So maybe we can find inside this torsion picture here some way to define modules that have a Weyl filtration, such that the multiplicities are given by the first generation, second generation, third generation character, so that at the end you arrive at tilting characters. So why don't we have some kind of well-defined intermediate modules here that are naturally canonically defined that give these patterns? So everything would be would happen inside the representation theory of this distribution algebra. The problem is this is not easy. If you look at the torsion coefficients, I can show it to you here. So this dot is there because there's a torsion 3, and here as well. You have torsion 3 here, and you have a torsion 9 here, which is good because the length of this leg is 9, but unfortunately here the torsion is 3 again. And so that should kind of tell you that it's not very easy to define these intermediate steps in this torsion picture. So, but now let's look at quantum arithmetics. So, okay, yeah. So here the idea is to replace the integers first by the ring of Laurent polynomials in one variable. So you replace the integers here. Then the prime p you replace by the prime, the ideal, which is, yeah, so this is the kernel of the map from Z to FP given by, if you evaluate V to 1, well, this is also, of course, the kernel of this map. So, and then you can localize at this prime ideal. You can do the same here. So that's very easy. So let me just write it down. So this is a quotient. So F and G are polynomials, and G of 1 is not divisible by P. So this is a nice ring. Check on my notes if I don't forget anything. And the integers here are replaced by the quantum integers, which are yeah, maybe I should say now I'm looking at this only at the simply lace case. Otherwise, you have to add some powers of V here. And this is actually, I mean, this is element. This is a real polynomial in Z. So v to the n minus v to the minus n is divisible by v to the v minus 1. This is in Z. And the nice thing is that there are many nice things. So of course you have the map from Z to Z where you evaluate v to 1. And the quantum integer will be mapped to the integer n again. Okay, so, but the quantum integer, this is something that is invertible times, you can rewrite it in the following way. So v to the 2n divided by v squared minus 1. Very easy, so it's something invertible. Very easy calculation. And you see this splits into cyclotomic polynomials. So L should divide 2n, but not be 1 and 2. So L is bigger than 3n. Then you have sigma L here. And this is the Lth cyclotomic polynomial. So that means, for example, so you see, 9 is of course 3 times 3, but quantum 9 is something invertible times sigma 3 times sigma 9. And so it splits into two prime factors, but they are different in this case. By the way, sigma p to the L, if you evaluate this at 1, this gives always p, independent of L. So this 3 goes, sigma 3 goes to 3, and this sigma 9 goes to 3. And now you can do just the same thing. And let me just tell you the what happens with our torsion. Here the torsion primes. Oops, I'm getting ahead of myself a little. Just delete this. The torsion primes are actually sigma 3 here, sigma 3, sigma 3, sigma 3, and here sigma 3 times sigma 9, sigma 3 times sigma 9, and then not sigma 3 but sigma 9, and this goes on. And now you actually see the generations appear, at least in the case A2. You can now ask for a sigma 3 torsion, then this gives you this leg, and this leg. And you can ask for sigma 9 torsion, which only gives you this leg, for example. So, I mean, these things are still conjectural because they're very hard to calculate. But this is the main idea. And now let's get back to the theory. Of course, what we did now with numbers, we can do with the algebras of distributions or the enveloping algebra. So, I want now to define curly D, curly Z as a subring in U QV. So this is the quantum group, the generic quantum group over over QV. So this is generated. Of course, I won't give the relations by some E alphas, F alphas. Excuse me for using the same notations here, and K alphas, alpha minus 1, and a lot of difficult relations. And this is Lustig's Z form. So this is generated over Z by again by these divided powers. So here, and then you have the curly, this bracket binomial coefficient that you can also define. Alpha is in pi and is bigger than 0. And this is defined over Z. This is Lustig's integral form of the quantum group. And now for any a Z algebra, so an algebra with an invertible element, you can define dA by base change. And especially, so most importantly, we have now DZP. So this is so curly. This is the quantum replacement of the algebra that we had before, and you can define V lambda and T lambda. I write everything curly if it's a quantum. So the Y module and the tilting module. For any lambda in X plus. And you can, as before, the same tricks give you the following. So you define can be O for this quantum group, no, sorry, the objects with a Weil filtration. And when you have a weight mu, you define these extreme cases, extreme spaces as before. And now the same lemma applies. So, for example, yeah, let me just write it down. So this middle space divided by this, this is a torsion ZP module. But now the torsion is much, much more difficult because this is not a principal ideal domain. Yeah, I mean, this is what we actually use. Another very interesting fact is that this quotient, it is annihilated by a product of sigma, so cyclotomic polynomials for some powers of P, certain powers of P. This is kind of surprising. I mean, not so hard to show, but well, it tells you once again that it's these cyclotomic polynomials that play a role in this quantum group business, and everything else is generic. But what is also very surprising is that the prime P, I mean, the prime P is still an element in CP, the number P. It doesn't occur as a torsion coefficient here. It's really only these cyclotomic polynomials. And the problem now is that, as I said, this torsion is super hard to understand because there's no elementary divisor theorem. So it's very hard to get an idea of what this mu min looks like inside m delta mu. So yeah, so let me just write, this is mu min, and it's very hard to understand the quotient. And I decided to write down some vague hope. But I have absolutely no good reason to believe that this hope is true, other than my, my optimism. If P is big enough, and big enough should mean that Lustig's formula holds, Lustig's irreducible character formula holds, then there are elementary divisors. So, i.e., the torsion is a direct sum of ZP divided by sigma p to the L1 times sigma p to the LR for some L1 LR in N. So so it is possible, and it would be very nice, that's the only thing I can say, if for P big enough, this torsion part is very easy to understand. Okay, but anyways, what we can do is well, that I guess is the last construction for my talk, is the following. So I want to approximate, I really want to give you approximations for these tilting modules. So how are these approximations defined? So if we have a subset in the natural numbers, then we can define m mu theta as kind of taking care of all torsion of sigma p to the L, where L is in theta. So what does it mean? These are all m in m delta mu, such that sigma p to the L1 up to sigma p to the LR m is in our minimum module for some L1 up to LR in theta. Okay, and now there's a definition. M, curly m I should write, curly m in O Weyl filtration over the quantum group is called theta standard. Theta standard if m mu takes care of these theta torsions, but not more. Okay. So this mu theta, it also lies between the minimal and the maximal module, and it's a specific module space inside there, and we can ask that this space is, well, coincides with this mu theta, and the theorem is the following. So for lambda in x plus and theta in n, there exists a unique object t theta lambda. Let's write this curly t, in O such that, well, first it has highest weight lambda, sorry, this is just free of rank 1, the highest weight space, and all the other weights are smaller. Then second, it is indecomposable. Indecomposable. And third, it's theta standard. So these objects exist on this quantum group level, and next theorem. Well, the things that I know about these objects is, well, if we don't have any torsion, if we don't kill any torsion, then we obtain the Weil module. So the quantum Weil module. If we look at the maximal subspace, then we have the tilting module, curly tilting module. 3. So one interesting thing is that they always have a Weil filtration by construction. And 4, if we just take one element, then this has the character of the corresponding tilting for the quantum group at p to the lth root of unity. Okay, so in principle now you have, because you have a Weil filtration, you can calculate all these Weil multiplicities and hope that this gives you some idea of the generations. As you can see, theta is just an arbitrary subspace of n. I think if you talk about first, second, and third generation, you should take the subspaces 1, 1 and 2, 1, 2, 3, 1, 2, 3, 4, and so on. But no one says that you have to do that. I mean, you can also only look at, yeah, I mean, one single element. Yeah, maybe, so these are called theta standard because every theta standard object, we just go a little bit up. So every theta standard object is actually a direct sum of those. So that's why I called them theta standard. These T theta lambdas are the indecomposable theta standard objects. Okay, I prepared a few more slides that contain the proof of this. I mean, it's kind of a construction, but my time is up. Thank you very much.
Well, thank you, Peter, for a lovely talk. Does anyone have any questions?
Yeah, SL3. Did I write A3 somewhere? I'm just looking at the chat right now. A2.
Oh, so I have a question. Can I ask?
Mm-hmm. Sure.
So I don't understand. So do you have some proposal for what K generation is?
Well, yeah. So so I would say the Weil multiplicities of these T theta lambda, where you take theta to be the set 1, 2, 3 up to your level of generation. I mean, you can count. I mean, there are these multiplicities, and they should maybe give the nth generation. So so these numbers, let me just write them down. You construct this module for 1 up to L for the interval and lambda, and then you look at these these multiplicities, and you get some numbers, and they could be related to the generations. But I have very little evidence for that. Even for SL2, I cannot really prove it. I can calculate, and it works until the computer gives up. But I don't have any evidence for this.
But you're saying that everything can be done in terms of the quantum group at the root of unity, which is
well,
which is something which I found that is not possible. But,
yes, and then, well, you have to take all quantum groups at all. So at the pth root of unity, p squared root of unity, p cubed root of unity.
Even then at seems to me that you cannot do, well, for when I look like you cannot do it, but maybe I'm
okay, then I would love to maybe discuss this. And
no, but then also the other question is for me, I think the equivalent problem was to find a category in which this K generation of simple modules is simple.
Yes.
Can you do that in your case?
No, so you know, that's what I mentioned earlier. I understand that you want an algebraic structure where the nth generation object is a simple or a tilting module. I mean, in this case, so I guess you asked, is this object, can it be, sorry.
No. This has nothing to do with tilting modules, just a K generation of simple modules.
Well, you can do something similar with simple modules. You can also interpolate between the simple module and the while module using these ideas. So what you obtain are G modules for the for this big quantum group, or over CP, or if you specialize for the group G. So that would be G modules, rational representations between the while module and the simple module.
Okay.
Are there any more questions for Peter?
I have a follow-up for George Lustig's question. So George's objection, I wonder if it's about the point 4 on this slide. Like, you only take L, it doesn't work, or do you mean something, a deeper obstruction even? So Peter was going to say that it kind of mixes all quantum groups at p to the e root of unity for e from 1 to L at simultaneously, something like this.
So if you put L equals 1, let me just, I mean, for L equals 1, you would get, you would get these legs. For L equals, if you only take L, you would only get these legs, but not the 3, not the 27 leg. You would get these 9 legs, but not the 3 legs. Here you get a 9 leg 2. But if you take 3, 1 and 2, you would get this picture. Does that answer your question?
Well, I think I understand what you mean, but then what I don't understand is whether if George still has an objection after this explanation.
Yeah, I would like to discuss this too, of course. Yeah. So, I mean, I talked to Jordi also about this, and I think it's strange that you can take arbitrary subsets of n to define these intermediate modules. And I don't know what is special about the subsets that are intervals starting from 1. I don't know what is special about them.
Well, it's strange to have subsets, but you explain why. It's because you have this different.
Because there's no order between sigma 3, sigma 9, sigma 27. So they don't divide each other. So they're completely independent.
Okay, well, maybe if there are no more questions, we can thank Peter again for his talk.
Thank you.